Good afternoon and welcome to our third Primavera webinar. Today we will hear about sea ice research and learn how sea ice changes affect our climate. And we are lucky to have three Primavera scientists who are experts on this issue today with us. First, just a short introduction. My name is Dragana Bojovic. I work in the Earth System Services group of the Barcelona Supercomputing Center. I think in any moment now we will also be joined by Erika Palin from Met Office. Erika and I will coordinate activities related to knowledge transfer and stakeholders engagement in Primavera. And this webinar series has the aim to share project findings and discuss them with stakeholders and users. Our first speaker today is Torben Koenigk. Torben leads the Global Climate Modeling Group at the Swedish Meteorological and Hydrological Institute. Torben is particularly interested in the Arctic climate, its variability and future change, and the potential impact on lower latitudes. And so, Torben, the floor is yours. Okay, here it is. Would you like, Torben, should I be sharing the screen, or would you like to do that?
I think it would be good if you would do it, because I'm connected via phone and I'm not sure if it will work.
Okay, sure.
So I hope you can hear me all. I will give more background on the observed changes in Arctic sea ice and climate. And this is really rather basic, and it seems that you're all relatively familiar with Arctic sea ice and Arctic climate processes. So maybe it's too easy for you, but I will go through it anyway. So I will talk about changes, also about causes of the Arctic warming, and some potential impacts. Next slide, please. Okay, I still see the same slide. Do you see the next one? Okay, very good. So the Arctic is not really clearly defined. There were different definitions for this region. It could be often it's defined as a region colder than 10 degrees in the warmest months, or the region north of the polar circle, or in climate science often use the area north of 60 degrees north or 70 degrees north, but also sometimes defined as north of the tree line. Anyway, it always includes the entire Arctic Ocean and some parts of the surrounding continents of Northern America, Russia, Eurasia, and Greenland. So this is a very big region, and the climate can be very different in this region. Please, the next slide. So on the left, you have the temperature, the minimum and maximum daily temperatures as a climatology from Ellesmere Island in northern Canada, the very most part of the Canadian archipelago. And on the right side, you see Nuuk and southwestern Greenland. And we see that in Ellesmere Island, we have winter temperatures between -30, -35 degrees, in summer around 0, slightly above. While in Nuuk, we have temperatures between -5, -10 in winters and 5 to 10 degrees in summer. So a warming of, for example, 5 degrees would mean different responses for sea ice and for the ecosystem, depending on where you are. If you have -30 degrees and you warm the air by 5 degrees, it probably doesn't matter too much. But if you're near 0, it could be a very strong difference, such a warming. Next slide, please. So this slide shows the observed temperature change since 1900, and in the gray areas there were not enough observations for the entire period. So, but what we see is that the Arctic is warming by most the fastest and the strongest, while the global mean temperature has been warmed by around 1 degree. In the Arctic, it's more than 2 degrees. In some local areas where the sea ice also disappeared during winter time, warming can be even much higher, up to 10 degrees. So the warming is the strongest in the Arctic, and that's what we call Arctic temperature amplification. Next slide, please. And this warming is strongly connected to a reduction of the sea ice. On the left side, you see September sea ice extent or concentration in the year 2012, where we had so far the lowest sea ice extent since the satellite data has been started. And on the right side, you see the same for 1980. So more than half, or around half of the area has disappeared of sea ice. And now, where we had sea ice before, we have a lot of open water. And especially if we then go towards autumn or early winter, this means strong differences in the interactions between ocean and atmosphere, and in the heat fluxes from the ocean to the atmosphere, leading to strong local responses, but it could also maybe affect the large-scale circulation and lead to remote effects on the climate. So next slide, please. The sea ice is not gradually being reduced, but there is a strong variability from year to year. And we see in this time series, which shows the Arctic sea ice extent in September, that especially since 1995, there was a strong reduction with the lowest value in 2012. Thereafter, some recovery, but on very low level. But still, both the area where we have ice can vary, and also the total amount can vary a lot, depending on the year, on the summer conditions, but also on the preconditions from the winter before. Next slide, please. So why is now the Arctic warming particularly fast? The main reason for this, which is normally mentioned, is the temperature ice albedo feedback. And this is showing it in a schematic. On the left side, we assume a pre-industrial Arctic Ocean, which is basically entirely ice covered, and 100% of the solar radiation that reaches the ice surface from this large part will be reflected by the white surface of the ice. Around 80% is reflected back to into the atmosphere, and only around 20% is used for melting of sea ice and warming the ice-ocean system. If we go to a global warming state, some of the ice has been melted, and now a large part of the incoming solar radiation is absorbed by the dark ocean instead of being reflected. And this is further warming the ocean and leading to additional sea ice melt. So we have a positive feedback, a warming, initial warming, so greenhouse warming leads to ice melt, to more open water, to less solar radiation, which is reflected, so more heat is kept in the ocean sea ice system, which then leads to additional warming and even more ice melts. Okay, next slide, please. But there were also other processes contributing to the Arctic amplification, not only this ice albedo feedback, and some are listed here. I will not go into detail here, but we can have increased heat transport in ocean and atmosphere, which transports heat from the lower latitudes to the Arctic, leading to especially strong warming there. Then we have a water vapor effect. If the air is getting warmer, it can take up more water vapor. If sea ice melts, we have a closer connection to the ocean and more humidity in the air. So water vapor is a greenhouse gas and leads then even to more warming also. Then we have a temperature effect. Often now, if we have sea ice in winter, we have an Arctic inversion, which means that it's colder at the surface than in the air above. If the sea ice disappears, also this inversion will disappear. So a lot of the heat is first used to warm the surface of the Arctic. And that's also the reason why we see such a strong warming at the surface, such a strong temperature amplification at the Arctic surface. But if we go further up in the atmosphere, we don't find such a strong amplification of temperature in the Arctic anymore compared to lower latitudes. Okay, next slide, please. What is then the impact of sea ice decline on lower latitudes? The last decades, you might have seen a lot of articles in the media, like the one on the top left from The Guardian: Arctic sea ice melt may bring harsh winter to Europe. So many cold periods have been linked to Arctic sea ice melt recently. And the reason for this is the temperature trend pattern on the top right. In winter between 1990 and 2013 is shown here, which shows a strong warming in the Arctic, but a cooling especially over central Siberia, but also in some other regions of lower and mid latitudes. And this temperature pattern has been linked to the sea ice reduction on the top, on the left, lower left. And this reduction, sea ice reduction, and the strong warming in the Arctic, so the process behind that is often suggested is that this leads to reduction in the temperature gradient between the Arctic and the lower latitudes, and consequently changes in the atmospheric circulation, which especially lead to more meridional winds, south, southwest, instead of south-north, instead of zonal winds. And particularly, it has been observed that at the Siberian coast, the pressure has been strongly increased, and this leads to cold air advection further towards Siberia. But there are hundreds of articles on this now, and it's not really a consensus on this issue. And the main problem is that observations are still short in the climate sense, and that the variability is very large. And I just want to give you one example for this on the next slide, please. Here you see the sea ice extent on the top in the Barents Sea in September, in November, and in winter, and everything goes down after around 1995. Then in the middle row, you see the pressure normally at the Eurasian Arctic coast, and this is increasing, and as a consequence transporting cold air towards Siberia, which we see in the lower row. So from this figure it seems to be relatively obvious. We have a decrease in sea ice, increase in the sea level pressure transporting cold air towards Siberia. But if we now add a few more years to this time series, then it's less clear. The sea ice extent area is not changing strongly anymore. It stays at a rather low level, but the sea level pressure normally returns to normal values, and so is the temperature over Siberia as well. So if we look at the entire time series now from 1980 to 2017 here, it's this connection between sea ice reduction and Siberian temperature is less obvious than if we only concentrated the period between 1990 and 2013, for example. So it's a bit unclear what will happen in future if the last 4 years are due to natural variability, or if the coldest trend before was mainly natural variability. So more research is obviously needed, and Steve will give more information on this in the third talk. But before, next talk will be given by Docquier. So that was everything from my side. Are there any immediate questions?
Thank you, Torben. I think then we can leave the discussion for later, and maybe now I would like to introduce David. David Docquier is a climatologist working at the Catholic University of Louvain, and David is working on the links between Arctic sea ice and ocean heat transport. David uses climate models and different kinds of observation to make this analysis. David, the floor is yours.
Thank you, Dragana. Can you hear me?
Yes.
Okay. So yes, now I will talk about the performance of Primavera models compared to previous models, and in the context of sea ice in the Arctic. So if we go to the first slide of my presentation. We have here a nice plot showing all the different models from the CMIP5 intercomparison, where you see the time series of sea ice extent in September from 1980 to 2100. So it includes historical and projection scenarios, especially the most extreme scenario in this case. And you see that first good news is that the models can reproduce the negative trend in sea ice extent. So you have a decrease in sea ice extent over time. The observations are in black and all the models are in color. But the bad news is that you have a very big intermodal spread. So you have a very large range in the model. So the uncertainty linked to sea ice is high in CMIP5. If we go to the next slide, then we see preliminary results of CMIP6, so the new intercomparison of models, global climate models. And we only show here results from 8 different models compared to 2 different observational data sets. The thermal spread is quite large between the different models. So it doesn't seem that in that respect, the model will do the simulation of the total sea ice extent. If we go to the next slide, then in the framework of Primavera, we want to have a look at the resolution. So we ask the question, does the resolution improve the representation of sea ice, for example? And to have a better view of the resolution of models, we can have a look at the 4 panels at the top here on this slide. And you see that going from 1 to 4, we increase the resolution in the models in both the ocean and on land. So if you increase the resolution, you have smaller grid cells, and so you represent better the climate in all components of the climate system. So you have a higher level of details. And at the bottom, you have a small scheme showing all the components of an Earth system model. In Primavera, we focus on so-called AOGCM, so atmosphere, ocean, general circulation models. And these include atmosphere, sea ice, land, and ocean components. So in our case, we focus on sea ice and especially the interactions with the ocean. So if you go to the next slide, in terms of Primavera, I've also put a time series of September sea ice area for the different models that are present in Primavera. So we have 7 different models with at least 2 different resolutions. And in black, we have the observations. So you see that all models, as for model comparisons, show a negative trend in September sea ice area. So you have a reduction of sea ice are for the low resolution models and the dashed lines for the high resolution models. And you see that generally when you increase the resolution in the ocean, then you decrease the area of sea ice. So for example, if you look at the blue curves, the solid blue line versus the dashed blue line, then you have a reduction in sea ice. And this is also the case, for example, for the green curve, another model. But in one case, it improves the representation of sea ice compared to observation, while in the other case, it doesn't improve the sea ice extent. So generally, it decreases the area of sea ice, but not necessarily improving the sea ice extent compared to observations. Next slide. So here we show the mean seasonal cycle of the same quantity, so the sea ice area in the Arctic, for all the different models for each month of the year. So it's running from January to December, from left to right, for the 16 different model configurations that we have in Primavera, and the observations are in black. So it's a bit complicated to see all different colors for the different models, but generally what you see is that improving the increase in resolution doesn't necessarily improve the results compared to observations, but it generally leads to a reduction in sea ice area. So when you increase the ocean resolution, you have a decrease in sea ice area. Next slide, please. So here we have different maps of sea ice area in one of the seas of the Arctic, so the Barents Sea. This is where you have a lot of changes happening right now in terms of sea ice area. You had a lot of high reduction in sea ice area over the Barents Sea over the last years. And when looking at the different maps, same results. You don't necessarily improve the representation of sea ice area in that sea when you increase the resolution. The observations are in panel I, so the bottom right panel, the observations. And if we look at the different models, the other panels, then we don't really see an improvement. But what we see when increasing the resolution in the ocean is that you have a higher level of details in the models. So if we go to the next slide, I showed you that with a higher ocean resolution, you have a reduction in the area of sea ice in the Arctic. Why is that the case? We make the hypothesis that this is due to an enhancement of the heat transport from the Atlantic Ocean. And this is due to both a strengthening of the currents at the surface and also an increase in the sea surface temperature. So on the left side, you have different maps of the models in Primavera, as well as the observations in the bottom right panel. You have generally an increase when you increase the ocean resolution. So going from A to D panel, or going from B to E, for example, then you see that you increase the ocean surface currents in the Barents Sea, and they are in better agreement compared to observations. The other thing, so on the right side, you have the difference in sea surface temperature between high resolution and low resolution configurations of the same model. So if you have red color, it means that you have an increase of the sea surface temperature with resolution. If you have blue color, it's a decrease in sea surface temperature with higher resolution. So when looking at the A, B, C panels, we increase the resolution in the ocean. You see that generally you have an increase in this sea surface temperature. In the last panel, D, we only increase the resolution in the atmosphere. And in that case, you don't really see a difference between the two configurations. So to conclude on this slide, with a higher ocean resolution, we have higher Atlantic Ocean heat transport, and this may lead to a reduction in Arctic sea ice area. So next slide. So this relationship between the sea ice area and the heat transport from the ocean is more pronounced in different Arctic seas, especially in the seas that are connected to the Atlantic Ocean, obviously. So for example, the Barents Sea, if you look at the panel F, and the Gin Seas, panel H. So all these scatter plots show the sea ice area versus the ocean heat transport. So when looking at the Barents and the Gin Sea, you really see a negative correlation between the two variables. So this means that when you increase the heat transport from the ocean, you decrease the sea ice area. in those specific seas. While if you look at the other panels, B, C, D, E, and G, you don't really see any relationship between the two variables. So if we go to the next slide, here on the top panels, we represented the sea ice concentration in March on the left side and in September on the right side for two different models, so a low resolution and a high resolution configuration of the same model. The first thing that we see is that if we compare the low resolution and the high resolution configuration, you have a reduction in the sea ice extent. And the second thing is that when we look at the bottom panels, these are the correlation maps between ocean heat transport computed in the Barents Sea and the sea ice concentration for every grid cell. So if we correlate those two, you see that you have negative correlations, especially in the Barents Sea. So this means that in the Barents Sea, in the case of March, especially in winter, you have with an increase in ocean heat transport in the Barents Sea, you have a reduction of sea ice concentration in the Barents Sea. In September, you don't see such a high anti-correlation because most of the sea ice has already disappeared during that time period. If we go to the next slide, this is a summary of what I said now. So Primavera is really the first multimodal project that aims at looking at the impact of model resolution on all the different components of the climate system, really in detail. What we see is that the spread in Arctic sea ice area, extent and volume is still present compared to previous model intercomparisons. So there is no real improvement so far compared to previous intercomparisons. But what we see is that with a higher resolution, we generally have higher level of details. This is logical. So this brings a better representation of the different processes happening everywhere on the globe, and especially in the Arctic. We saw that having a higher ocean resolution leads to reduced Arctic sea ice area, and this is probably due to an enhanced heat transport from the Atlantic Ocean. And we also saw that some key regions, like the Barents Sea, experience a stronger influence of the heat transport from the ocean on the Arctic sea ice. So we need more research to understand all the details of the impact of model resolution on Arctic sea ice and the links with the ocean. So if you have any quick question on this small presentation, please ask me now.
Hey, yeah, I have a question.
Yeah.
Can you hear me?
Yeah, and who is speaking?
Evelien Dekker from Stockholm is speaking.
Okay, yes, yeah, we can hear you. Yes, please go ahead.
Yeah. I was looking at those scatter plots where you scatter the sea ice area against the ocean heat transport. And in that figure, I saw heat transport across 17 north. Is that right? So the other one was about heat transport in the Barents Sea opening, right?
Yeah, that's right.
Yeah. So I was wondering if these heat transports, are they instantaneous or are they lagged? And because maybe that matters because the ocean is maybe not that fast.
Yeah, that's a good question. In that case, in the case of those scatter plots, it's the annual mean ocean heat transport. So it's not, there is no lag here. So it's really the mean heat transport over 1 year versus the sea ice area in March. And
in the same year?
During the same year, yes. So each dot corresponds to 1 year.
Yeah.
Yeah.
Yeah, because I think it would be interesting to look at that for different time lags.
So regarding the correlation between heat transport in the ocean and the Arctic sea ice, we had looked at the lagged correlation during different months of the year, but we didn't find such a high anti-correlation compared to using the annual mean in ocean heat transport. So it's really the mean signal in the Atlantic that matters. But when looking at the heat transport specifically in the Barents Sea, then you might see, we haven't already looked at that. We only looked at the annual mean heat transport, but you might have a higher negative correlation when doing that. Yes, that's a good question.
Yeah, let's move to the last presentation. So with us is Steve Delhaye, who is also working at the Catholic University of Louvain. Steve works on the climatic impacts at mid-latitudes due to Arctic sea ice loss. Steve uses several climate models to study these impacts. Steve, can we hear you?
Yeah, so sorry, it's François Massanet here. We are going to make the presentation from my office because it looks like they have sound connection problems.
Okay, is Steve with you?
Yeah, it's right beside me.
Yes, can you hear?
Perfect, excellent, we can hear you very well. Yeah.
Okay,
Steve,
perfect.
please go ahead.
So hi, I'm going to talk about the impact due to the change in the Arctic sea ice. So if you go to the next slide, so the first thing we can wonder is how can we see the climatic impact due to Arctic sea ice loss. So the first thing we can use are the observations, but as Torben said in the beginning, is observations are short and the variability is very large. So to solve this problem, we can use climatic models. And in these climatic models, we can compare two different types of experiments. So the first experiment here, called the control one, has a constant forcing of a specific year. And here in the PRIMAVERA experiment, this year is 1950. Then the model runs several years and simulates the climate as 1950. And in this graph, we can see the Arctic sea ice extents for this simulation here in blue, so from January of the first year to March of the second year. And the second experiment, called the perturbation run, has also a constant forcing of 1950, but with the albedo, where we change the ice albedo. Indeed, we replace the albedo of the sea ice with the albedo of the ocean. And this change produces a melting of the sea ice. And we can see this experiment here in this graph in red. And by comparing with the blue curves, we can observe an Arctic sea ice loss, and mainly in summer. So these experiments last only 15 months to understand the impacts at short-time scale. And we have 40 different numbers of perturbations and control to see which climatic impacts are robust or not. So this is why we have several lines, blue lines and red lines. So if you go to the next slide, please. So to understand better the climatic impacts due to sea ice loss, we have several advantages here. So we have first two different climate models, and we will have a third one in the next weeks. So having a multimodal approach is an advantage because each model can have different responses due to different model physics and parameterization. And then if we have a same response for different models, the robustness is more important. Secondly, we have two different horizontal resolutions for each model. Then we could perhaps see if a better horizontal resolution can improve or not the possible responses due to Arctic sea ice loss. And as I said, we have 40 members for each experiment and to take into account the internal variability of the climates and then have robust responses due to Arctic sea ice loss. And finally, each model has the same experiments, so we can easily compare them. But the Arctic sea ice reacts differently even for the same experiments. And if you go to the next slide, we can see that, so here we have on this graph, the Arctic sea ice extends for two models. So on the top, we have the ECM model at high resolution, and on the bottom graph, we have the CNRM at high resolution. And we can see in this last one that we have a total disappearance of the Arctic sea ice in summer, so for the perturbation runs. So, and we don't have this in the ECMWF model, but we are still going to compare them. And to see the climatic impacts, we are going to compare the perturbation experiments, so in red, where we have sea ice loss with the control experiments. And on the next slide, we can see different maps. So the maps represent the change in the surface temperature in summer. So for the ECMWF model on the left and CNRM on the right, at high resolution at the top and low resolution at the bottom. And the dots represent where the response is statistically significant at the 10% level. We can see an important Arctic warming due to Arctic sea ice loss, with an increase higher than 2 degrees, and in fact it's even higher than 10 degrees over Central Arctic. We can also see a more important extent of warming to mid-latitude in the CNRM model compared to ECMWF, and this is due to the more important sea ice loss in this model with a total disappearance in summer. And now if we look over Europe, we can see slight warming, but like this it doesn't seem to be obvious. So on the next slide, I took a box over Europe and I computed the probability density function. So here for the surface temperature in summer. And so for the control one in blue and for the perturbation one in orange. And we can observe, so from the control one to the perturbation, we can see a shift to the right of all the distribution, so and for all the models. So this means a warming of all the distribution. So with an important Arctic sea ice loss, the probability to have hot summers increases. But in fact, this warming is not homogeneous throughout the European continent. And we can see this, yes, on the slides. So here we have a zoom on Europe, so for the surface temperature in summer. And we can see that the response higher than 1 degree is mainly located in Northern Europe. And in other regions, we can also have this important warming, so it's in 1 degree, but it depends on the model and also on the resolution. So for example, we can see on the ECMWF at low resolution, we can see an important warming over Eastern Europe, and in the CNRM at low resolution, this is more on the Western Europe. So for the next slide, if this is so the maps for the surface temperature responses, but now in winter, we can still observe so this important Arctic warming. And if we look now over Europe, so the warming seems to be less obvious compared to summer. So we observe even some cooling in the ECMWF at high resolution and also in the CNRM at low resolution. And moreover, we have less dots over Europe, so which means that the internal variability is higher compared to summer. And moreover, we have also some cooling events at mid-latitudes. So this is the case here over Eastern Eurasia, and this is robust. And this pattern looks like what Torben showed in the observation. So then according to these models and to these experiments, the observed cooling over Siberia could be due to Arctic sea ice loss. But the problem is other experiments and models show the opposite. So it's still difficult to confirm that this cooling is only due to Arctic sea ice loss or it's mainly due to internal variability. So now on the next slides, we can have a look here on the precipitation responses. So here in autumn, we can clearly see an increase over the Arctic. And this increase is high in autumn because the heat and the moisture going from the ocean to the atmosphere is higher during this season. And if we look at over Europe, we can observe less intense responses. And moreover, we observe some divergent responses between models and between the resolutions. And also we have few dots, so this is not statistically significant, which means that the internal variability is also quite high, and for the precipitation, this is higher than the temperature responses. So I have also tried to see the impact of sea ice loss on the external precipitation events. So this is for the next slide. So yes, thank you. So here for the precipitation events, here it's not shown, but there are no robust change in the intense precipitation response, but they are for the droughts. Indeed, these maps represent the change in the longest consecutive dry days, here for the month of November on the left and December on the right. So this is only for one model, so for the ECMWF model at high resolution on the top and low resolution at the bottom. So we can observe an increase in the duration of droughts in late fall, so mainly over southwestern US, with an increase up to 3 days over this region. And this result is quite similar to what Zvijanovic et al. Has observed in 2017. This is less obvious, but an increase up to 2 days is observed also in Europe, and only in low resolution in November. In the other months and other resolution, this is not statistically significant. But we can say that Arctic sea ice can increase the drought duration over some mid-latitude region, like southwestern US. Finally, so for the next slides, so for the question of comparing the resolution, we can notice here that the extent of the atmospheric warming is more important at low resolution compared to high resolution. So we can see that on these two graphs, which represent the extent of warming higher than 2 degrees. So for the low resolution in red and high resolution in blue, and we have the ECMWF model at the top and CNRM at the bottom. So for both climate models, the low resolution has a higher warming extent. So the red curve is above the blue curve. But unfortunately, we cannot say that the climatic responses generated by the high resolution model are better than the low resolution. But normally, high resolution represents better some phenomena, such as atmospheric blocking, which are the cause of extreme events such as the drought, as I showed you just before. Then normally, high resolution should have better responses for this variable, but until now, I cannot prove it like this. So additional research needs to be done for this. So yeah, that's all for my presentation. Thank you, and if you have any questions.
I actually have a question about which sea ice model is used in the ECMWF version now.
The sea ice model it's LIM 2.
LIM 2, right?
Yeah. Yeah. So no, only one ice category.
Yeah, I think.
That is something, yeah, maybe to continue on that question. In Primavera, we have 7 different models, and 5 of them use NEMO, either with.
Yeah, exactly. I guess the goal is to focus on the resolution impact, because if you also change the sea ice model or anything about the sea ice parameterization, you don't know if it comes from the resolution, or?
Yeah, that's right. That's right. So it's not easy. Yeah, what I showed in my presentation, I think it was quite robust among the models that we studied. But if we include other models using other ocean and sea ice models, but yeah, okay, there were 2 other models using other ocean models. So it seems to be robust among them.
But the impact of the resolution on the ocean heat, was the total ocean heat content changed when you switched from high to low resolution, or was it only the local heat content that changed in the?
So it's the total ocean heat transport, so including contribution from the eddies.
Yes, exactly. So so now the SST and the currents were, or the SSTs were higher and the currents were stronger into the Arctic in the higher resolution, if I understood it correctly.
Yes.
But the total ocean heat content did not change. It was just how it was exchanged now better by the, or better, like different by the eddies.
Yeah, the heat content, yeah, it might, yeah, I've not computed the heat contents of the ocean, but I guess it's also higher with the higher resolution. I don't really understand your point here.
No, it's just a curiosity if the increased resolution.
Yeah.
I guess there is nothing changing about the initial condition. So then it's only how the heat is redistributed in the ocean that is changed in the higher resolution version.
Yes, yes. the hypothesis is that when you increase the resolution, you better define the boundary currents, especially the Gulf Stream and the main currents going to the Arctic. So you really strengthen those currents, and you increase the SST in those currents, and that leads to an increase in the heat transport.
Yeah. Okay, thanks.
If there are no further questions, I would like to thank our speakers today. It was a really great update about what scientists are doing in Primavera. And I would like to thank all the participants